Welcome to the next session on removable singularity. We are going to see the definition of removable singularity and its examples and two theorems related to removable singularities. As I explained in the previous video, removable singularity is a one if f of z is expanded as a Laurent series about the singular point z equal to a has no principal part. What is the principal part in Laurent series? The negative powers in the expansion of Laurent series is said to be the principal part. If there is no negative term, what happens to f of z in the expansion of Laurent series? It becomes summation n equal to 0 to infinity a n z minus a whole to the power n when we expand about the point z equal to a, where a is the singular point. Now when we expand this, it is a0 plus a1 into z minus a plus a2 into z minus a the whole square, etc. And this is a polynomial in z minus a the whole square. At the point z equal to a, which is a singular point, the derivative of f of z exists at the point a because it's a polynomial. Now this f dash of z is defined at z equal to a. So now the function becomes analytic at z equal to a. But we started with a is a singular point, and if we expand f of z about z equal to a as a Laurent series, then it has no principal point. But the starting point is a is a singular point for f of z. That means f of z is not analytic at z equal to a. But when we expand as a Laurent series, what happens is there is no principal part. Therefore, the property of singular point has been removed from f of z. The property of singular point of z equal to a for f of z has been removed. Therefore, this particular point a is said to be the removable singularity, and the function becomes analytic at z equal to a. That's why we are calling a as a removable singularity. Now what happens if I find limit of f of z when z turns to a? It becomes a0. So by defining my f of a to be a0, I can make my function f of z as analytic at z equal to a. Whenever this is a finite constant, then the analyticity of f of z will not be affected at the point z equal to a. So we are very particular about the first term a0, and at the point z equal to a, if f of a is a0, then f of z will become analytic at z equal to a. So a function which is not analytic at z equal to a now comes to the point that f of z is analytic at z equal to a because it has no principal part. So the singularity has been removed from f of z. So such a singular point is said to be removable singularity. So in a simple way I can say that a point z0 or a is said to be a removable singularity. Then that function becomes analytic at z equal to a after expanding that one as a Laurent series. Now let us see few examples. Example 1, f of z equal to sin z by z. Now let me equate the denominator to 0 to find the singular point. Now 0 is a singular point and it is a isolated singularity. Now is this singular point is a removable singularity? Let us check. What is sin z? You keep 1 by z as it is. The expansion of sin z is z by 1 factorial minus z cube by 3 factorial plus z power 5 by 5 factorial minus etc. Now multiplying this 1 by z, it will be 1 by 1 factorial minus z square by 3 factorial plus z power 4 by 5 factorial plus etc. Now here there is no negative powers of z minus 0. No negative powers of this about the point 0, the singular point, the singular point. So since it has no negative powers, then the function will be analytic at all the points. Therefore, this function f of z becomes analytic at z equal to 0. Therefore, this z equal to 0 is said to be a removable singularity because it has no terms in principal part, no negative powers of z minus 0. Shall we check the criteria of this one, whether we are getting limit of f of z as a naught? Yes, obviously, when I find limit f of z, when z turns to 0, it becomes 1 by 1 factorial. All other terms become 0. So, by defining f of 0 to be 1, I can make my f of z as an analytic function. Second example, let me consider an example f of z equal to z minus sin z by z cube. Once again, let me expand sin z by 1 factorial minus z cube by 3 factorial plus etc. Z minus z becomes 0, multiplying minus, it becomes z cube by 3 factorial minus z power 5 by 5 factorial. Now multiply this 1 by z cube, it becomes 1 by 3 factorial minus z square by 5 factorial plus etc. Now there is no negative powers of z. Here z equal to 0 is the singular point. Equating z cube equal to 0, you will be getting z equal to 0 as a singular point, isolated singularity. Now this is an expansion about z equal to 0, which has no negative powers of z minus 0. Therefore, there is no principal part. Therefore, this becomes a removable singularity of f of z. Now, let us check the condition. What happens if I find limit of f of z when z turns to 0? What happens when I apply the limit? When I apply the limit, z turns to 0. From this, all the terms become 0. I will be left with 1 by 3 factorial. So, by defining f of 0 to be 1 by 3 factorial, my f of z becomes analytic at z equal to 0. Now, we have seen what is a removable singularity and its example. Now, let us move on to theorem 7.4. The statement is let f of z be a function defined in a region D of the complex plane except possibly at a point A belongs to D, and let A be an isolated singularity for f of z. So from this statement we came to know that A is the isolated singularity for f of z, and f of z is defined in the region D except at A. The second point, A is a removable singularity for f of z. This is the criteria. We are going to see a criteria for a point to be a removable singularity. A is a removable singularity of f of z if and only if there should exist a complex number a naught such that by defining f of a equal to a naught, now the function f of z becomes analytic at a. What we have seen previously in the example, the limit is when z turns to 0, it becomes 1 by 6, so that my function f of z becomes analytic at z equal to a. The same criteria is imposed in this theorem. Now let us list what are all given. What are all given in the theorem? It is stated that f of is defined in D except at a point a belongs to D. A is an isolated singularity for f of z. I have to prove it is a if and only if criteria. So let me take the if condition first. What it is given there? I am going to take A as a removable singularity for f of z, and I am going to claim that whenever I define f of a to be a naught, the complex function f of z becomes analytic at a. Okay, let me start with the given condition. A is a removable singularity for f of z. When it is a removable singularity, according to the definition of removable singularity, there should not be any principal part in the neighborhood of a. So f of z can be expressed as summation n equal to 0 to infinity a n z minus a whole power n. After expansion, it becomes a naught plus a1 into z minus a plus a2 into z minus a the whole square plus etc. Let me apply limit z turns to a on both sides of this. When z turns to a, all the terms starting from the second term becomes 0. So I will be left with only a naught, which is nothing but f of a. So by defining f of a equal to a naught, now my function becomes analytic at a. Now coming to converse part. What is its converse part? What I am going to take? I am going to define f of a to be a naught, and I am going to consider that f becomes analytic when I define f of a equal to a naught. What I have to prove is a is a removable singularity for f of z. How I am going to prove that it is a removable singularity? According to the definition, I should show that the principal part of f of z contains no terms in Lorentz series expansion of f of z about z equal to a. But my function f of z becomes analytic in the neighborhood of a whenever I define f of a equal to a naught. So my function is analytic function. Whenever my function is analytic about a point z equal to a, then it can be expressed as a Taylor series about z equal to a. So what is the Taylor series for f of z about z equal to a? It will be in positive powers of z minus a. Now, since it's a Taylor series, there won't be any negative powers. So the principal part has no terms. Therefore, a becomes a removable singularity for f of z. So hence, we proved that the criteria for a point a to be a removable singularity. Next comes Rimas theorem. The theorem states that f be a function which is bounded and analytic throughout a domain 0 less than mod of z minus z naught less than delta, that is in the neighborhood of z naught, then either f is analytic at z naught or else z naught is a removable singular point of f. So what are all given? F is bounded, okay, f is analytic in the domain, specified domain. What's the claim? I have to claim either f is analytic at z naught or else z naught is a removable singular point of f of z. Since it is stated that it is analytic in the neighborhood of z naught, there is no doubt f is analytic at z naught. So no need for the first criteria to be proved since it is directly given in the statement. The only thing is, I have to prove that the either case Z0 can be a removable singular point of f of z. Suppose z equal to Z0 is a singular point means, then I have to prove that this Z0 must be a removable singularity in the case of f, whenever f is bounded and analytic in the particular neighborhood of Z0. Okay, what I am taking Z equal to Z0 as a singular point. What I have to prove? I have to prove that Z0 is a removable singularity. For proving Z0 to be removable singularity, what I have to justify? I have to justify there is no principal part in the Lorentz series expansion. This is the principal part. What I am going to do is I am going to prove that this Bn becomes 0 for all n. What happens if this Bn becomes 0? All the negative powers of Z minus Z0 becomes 0. So when there is no Bn means I will be left with only positive powers. There won't be any principal part. Automatically Z equal to Z0 becomes a removable singularity. So my claim is I am going to prove that my Bn is equal to 0 for all n. What is Bn? Bn is 1 by 2 pi a integral over c f of z dz by z minus z0 whole to the power minus n plus 1, where c is the circle, modulus of z minus z0 equal to r, as we have seen in Lorentz theorem. Okay, in order to prove that Bn equal to 0, I am going to find the modulus value of Bn. Since f is bounded, modulus of f of z will be less than or equal to m in the specified region. So let me take modulus on both sides of Bn. So mod of I becomes 1. So it becomes 1 by 2 pi into mod of this integral. We have already learned from the theorem, modulus of integral over c f of z dz is less than or equal to m into L. That is theorem number 6.2. Modulus of integral over c f of z dz is less than or equal to m into L, where m is the maximum value of the integrant and L is length of this curve C. Okay, now I have to find modulus of this one. As I stated, f is bounded and modulus of f of z is less than or equal to m. So this is less than or equal to m. What about z minus z0? Is equal to r. Therefore, it is r to the power minus n plus r to the power minus n plus 1. Now, the modulus of the whole integrant is m by r to the power minus n plus 1. L is length of C. What is C? C is a circle. So, its length is its circumference. Its radius is r. So, its circumference 2 pi r. Cancelling 2 pi and r, this becomes m r per n. Now, I am going to discuss what happens if the radius is less than delta. That is very small. When I take a very small radius, what happens? That is r approaches 0. When r approaches 0, modulus of, that is limit r turns to 0, mod of Bn will be less than or equal to 0. Modulus value cannot be less than 0, therefore it will be equal to 0 when r turns to 0. Mod of Bn equal to 0 means Bn will be equal to 0. So this is true for all n. Hence, when I substitute Bn equal to 0 in Lorentz series, there won't be any principal part. So f of z has no principal part. When there is no principal part, z0 is to be a removable singularity. Hence the theorem. So we learnt two theorems, two properties related to removable singularity. The next video we will see poles.